Welcome back to Applied Machine Learning. We have just seen our first supervised learning algorithm, which was a linear model learned using gradient descent. In the next video, I want to look at a different way in which we can fit a linear model. In practice, the gradient descent approach that we just saw is not the best way that we have in order to find and optimize the parameters of a linear model. In this video, we are going to see a more practical approach, which is based on an approach called the normal equations. And this will give us our first non-toy supervised learning algorithm, which is called ordinary least squares. To start, recall the definition of the gradient, which is an important tool from calculus and optimization that we have used in order to define our first optimization algorithm called gradient descent. Essentially, the gradient, denoted in this form, is the vector of partial derivatives of the function f at the point theta 0. And the gradient can be seen as giving the direction, or it can be used to obtain the direction of steepest descent for a function. And by following this direction of steepest descent, we can iteratively minimize the function. In this video, we will see a new application of gradient descent that is going to give us an even better algorithm that will be faster in many applications. As in the earlier videos, we are going to be using the UCI diabetes dataset as our demo. Recall that the diabetes dataset is the dataset of patients for which we have a set of measurements such as the body mass index, and we have a quantitative risk score, the score for diabetes risk, and our goal is to predict diabetes risk from an individual's measurements such as BMI. Here I have again loaded 25 points from this dataset, and I'm visualizing in 2 dimensions the relationship between body mass index and diabetes risk. In order to define this new algorithm, which is going to be ordinary least squares, I first want to start with some notation. The first set of notation that I want to introduce is something that is called the design matrix. The design matrix is essentially just a convenient way of representing our training data set. We know that each of our training instances, each of our training examples has an input x, which is a d-dimensional vector. The design matrix is simply the concatenation of all of these vectors along a second dimension. Here is the definition of the design matrix, and you can see that it's nothing more than the input vectors being put as in a row form and stacked one on top of the other. In other words, X is a matrix of dimension n by d, where n is the size of our data set and d is our dimension, and the entry, the ith row of this matrix corresponds to the ith input object, to the ith vector of features, and the column j corresponds to feature j. So in the cell ij of this matrix, or I guess in this example, in row 2, column 2, we have the second dimension of the second input vector. We can obtain easily the diabetes matrix for the diabetes dataset. In fact, the dataset already comes in the form of this matrix, and this is what it looks like. These are the first 5 entries in this matrix, and you can see here that each row corresponds to a patient, and each column corresponds to a different feature or attribute. Another part of this notation that I want to introduce is also the following vector, which is simply the concatenation of all the targets that we have in our data set. We have simply placed them in a single column vector here. So we just stacked all the targets that we have. The n targets in our data set are placed here in a column, and now they become a vector. This is another piece of notation that I want to introduce. Now, using these two bits of notation, I am going to define these are going to be really crucial to define our algorithm. This algorithm that I'm going to introduce will also be optimizing the mean squared error. Recall that the mean squared error is simply the squared difference between the true target for any given example and the target that is predicted by our machine learning model. So in other words, we are looking for a set of parameters theta, which on average explain the data well. We have already seen this form, but we can now use we can use the notation that we just introduced to write it in a more complicated, in a more compact form that uses matrix notation. So our objective here, here it says RSS, the residual sum of squares, which is just another name for the mean squared error. We can write it as follows. You can convince yourself that this notation here is equivalent to the notation that we have here. Essentially, essentially what we are doing here is we are multiplying our design matrix by the vector of features, which produces another vector whose with n rows, or with n components, it's just a vector, and the result of multiplying basically the ith component of this vector will simply equal this dot product. This is just a definition of a matrix vector, the definition of matrix vector multiplication. And now we're going to have the vector of y's, the vector of these components, and so the subtraction of these two vectors is going to be another vector of dimension n, whose ith component will equal exactly this term that's within the parentheses. And now, in order to obtain this equation, we can simply apply the dot product of these two vectors, and by the definition of the dot product, this will equal exactly this expression. So in other words, here we have rewritten the mean squared error in this particular form, which is simply a dot product between two vectors that perform the same operation, but we're just writing this using a more compact matrix notation. And finally, another way of writing the same expression involves the following notation. This is these two bars here. They describe what is called the Euclidean norm, and the Euclidean norm is simply one way of measuring the distance between two vectors, and the definition of the Euclidean norm is just the dot product between these of the squared Euclidean norm is the dot product between these two vectors. Here we have just applied the definition of the Euclidean norm. These are two equivalent ways of writing the same thing, which you may see in different machine learning textbooks, and they are equivalent. So in this slide, what we did is we rewrote the mean squared error in this vectorized form. Now that we have written it in this vectorized form, we can use a little bit of algebra to derive a gradient for this objective. Now, recall that our mean squared error objective has the following form, and so now we are interested in computing the gradient of this expression. So again, this will be the gradient of the entire mean squared error for the entire data set. In these few lines, we do a few simple algebraic derivations. Here in the first line, we are simply multiplying each term on this side, but with each term on this side. So x theta, essentially this dot product equals the dot product of x theta with x theta, of x theta with y, y with x theta, and y. Here, this is just really simple algebra. Now, since we're taking a derivative and this term is constant, we can remove it. And we can also see that these two terms are the same. Here we're using the property that A transpose B equals B transpose A to merge these two terms into this term multiplied by 2. And now we want to obtain the gradient of this expression, which is, again, this is a this number here is a scalar, but it's a function of the set of parameters theta, and we can apply the rules of matrix derivatives to obtain an expression for this vector. So we are going to use two rules from matrix calculus. The first one is that the gradient of B transpose X is just equals B. You can easily verify this by just working out the partial derivatives of this equation and seeing that each partial derivative, the partial derivative with respect to X sub I will just equal B sub I. Hence this holds. And similarly, a really similar exercise can be used to show that the gradient of an expression of this form equals this. And again, this can be easily shown by writing out explicitly the matrix, the partial derivatives. And so applying these two identities in this line, we obtain the following line. And then we just, the twos cancel out. And we have the following expression for the gradient of the mean squared error in a vectorized form. All right, so far we have done a lot of matrix manipulations to obtain this gradient. Now we can use this gradient in several ways. We could use it to perform gradient descent, but instead we are going to use it in a different way now. You know from basic calculus that at the minimum of a function, the gradient takes the or the derivative takes the value 0. We've seen a simple example of this in our first in the first video of this lecture, where we plotted a few derivatives for the one-dimensional quadratic function. That was a simple example, but more generally for a multidimensional function, in a way that's really similar to that early example, the gradient at the minimum of the function equals 0. So this gradient here would equal 0. Hence, at the minimum of this quadratic function, this expression here would equal 0. And furthermore, because this is a quadratic, because j is a quadratic function here, we know that this is it's a simple fact of quadratic functions in that they only have one minimum. And so if we can solve the equation 0 equals this, if we can solve this for theta, then we can obtain a closed form expression for the minimum of this objective function. In other words, what we do here is we set the following term to 0, and now rearranging terms, we obtain the following equation, which is called the normal equation. Now, since this is since both the left-hand side and the right-hand side are vectors, they define actually a set of linear equations. Hence, they're called the normal equations in plural. So the theta that satisfies these equations has to be the minimum of the objective function that we're minimizing. This has to be the theta that minimizes the mean squared error. And we can solve for this theta by simply multiplying on both sides of the equation by the inverse of the matrix X transpose X. And now doing this, we obtain a closed form expression for theta star, which is the minimum of the mean squared error. So using all the derivations that you have seen, we have obtained a simple form for the minimizer of the mean squared error, and it is simply a product of a few transformations of our design matrix that we have defined earlier. I want to add just one additional note. In order for this to work, this matrix here, X transpose X, has to be invertible. It will often be the case, most often in applications this will be the case, and when it is not the case, there are simple ways of addressing this issue, and we will see we will see one way of doing this in the next few lectures. Alright, so here we have defined the normal equations and their solution. Let's now look at how we can implement this in practice. We can apply the normal equations very easily to our UCI dataset using NumPy, and in fact it's just one line of NumPy. So here I have an expression for theta star, which I'm calling here theta best, and this is simply the implementation of the normal equations in one line of Python. So running this equation, we obtain a value for theta best, and now with a little bit of pandas in order to make it prettier on the screen, I'm displaying the values that it's assigning to these different parameters. So these are the values that theta star assigns to each one of our terms here. And now using this new set of parameters theta best, we can make some predictions. So here I am going to load again 3 data points that are distinct from our training set. And these are the same 3 data points that we used in our earlier examples. And I'm going to generate predictions for these new data points using our new set of parameters theta best by simply multiplying these also form a design matrix with three inputs, and again I can just do the dot product to obtain predictions for these training examples. And now I can visualize both the data set and our 3 data points here. And you can see that the predictions here which are given by the red cross are indeed very close to the actual true values, which are the red dots. So now here, with only a few lines of Python and NumPy, we have implemented a real algorithm called which is called ordinary least squares. And this is going to be our first non-toy supervised learning algorithm. In practice, this is often preferable to the gradient descent approach, since it doesn't really require any tuning of parameters such as the learning rate, and in practice it just requires solving a set of linear equations for which there are many effective linear algebra algorithms and really efficient implementations that we can use. And so when you run the linear regression model or the linear regression object in the scikit-learn.linear models library, behind the scenes it implements the few lines of NumPy that I just showed you. And so now this slide summarizes what is the ordinary least squares algorithm. It uses the notation that we have seen earlier. So ordinary least squares is a supervised learning algorithm, and specifically it is aimed at regression problems where y is continuous. In practice we could apply it for classification, but we will see much better approaches later on. It finds parameters within the set of linear models, and it chooses parameters which minimize the mean squared error. And it does so by using the solution to the normal equations to obtain the parameters which optimize this mean squared error. So the optimizer here is a solver for the normal equations. So this here is our first non-toy algorithm, and we will soon see ways of using this algorithm to derive even more interesting and more sophisticated algorithms, both in this lecture and in later lectures as well.